percentage yields and atom economy. Using Chemistry Explained depends upon your participation. Make sure that you are writing notes and completing tasks with pen, on paper or on tablet as you move through the lessons. Go at the pace that suits you. Skip forward, move backwards where you think necessary. Most importantly, when prompted, pause the lesson. Complete the task, but taking your time thinking the problem through. When you're ready, come back to the lesson and check your work before moving on. So we'll start with percentage yield, move on to atom economy, and then look at issues of sustainability. The first idea in percentage yield is that of actual yield, which is the amount best thought of in terms of numbers of moles of product that is measured to have been made. So if we have reactant A and B making product C, we need to measure the quantity of product C, the mass, the gas volume, the volume of solution. I strongly recommend that in all cases those physical quantities are converted into a number of moles. So convert the mass of product into a number of moles, the volume of gas product into a number of moles, the concentration and volume of solution into a number of moles. We now need to talk about theoretical yield. This is the amount of product one would expect to get on complete reaction of the reactants or the limiting reactant. So if we take an example of hydrogen and nitrogen forming ammonia, we've got a mole ratio of 3 hydrogens to 2 ammonias. We can calculate that from 6 grams of hydrogen, if they react completely, we'll get 34 grams of ammonia based on 6 grams of hydrogen being 3 moles. 3 moles makes 2 moles. 2 moles of ammonia, well, each mole is 17 grams molar mass, so 34 grams. So we would expect the theoretical yield of ammonia to be 34 grams. But maximum theoretical yields are often not obtained for 3 reasons. Firstly, as in this case, I hope you recall that the Haber process, hydrogen and nitrogen forming ammonia, is an equilibrium. It's a reversible process. So as soon as you're making ammonia, you're going to reform hydrogen and nitrogen. They coexist at equilibrium. So we're not going to obtain that 34 grams. Side reactions producing byproducts may exist. Not particularly in this example, but in many others. And procedures may result in loss of product, particularly laboratory procedures where products may be simply left behind in filter papers, etc. So, the maximum amount that could be formed is called the theoretical yield. Unlikely to be obtained for more than 3 reasons, but these 3 reasons are prominent. So we now move to the topic in the lesson heading, percentage yield. So this is a numerical comparison between actual yield and theoretical yield. So the amount as measured of product and the maximum amount of product as calculated from the balanced chemical equation. So we got a formula which you just simply have to know. Percentage yield is actual yield divided by theoretical yield, and we turn it into a percentage rather than a fraction by multiplying by 100. So here's an example. Based on the previous slide, if the actual yield of ammonia on the reaction of 6 grams of hydrogen was only 11 grams, rather than the theoretical yield of 34 grams, can you pause and calculate the percentage yield? I'm about to reveal, so make sure you've done the calculation. Very simple. The percentage yield is the actual yield, which we are told is 11 grams, divided by the theoretical yield, which we calculated on the previous slide to be 34 grams. Multiply that fraction by 100, comes to 32.4. So we are able to put in the masses because, as you probably realize, if we turned 11 grams of ammonia into moles, we'd divide by 17. If we turned 34 grams of ammonia into moles, we'd divide by 17. So the 17s cancel out. So if you have got mass data in both cases of actual and theoretical yield, you can just put those into the percentage expression, because of course the molar masses would cancel out in that calculation. So I'm going to give you a couple of problems. First one, very straightforward. 6.63 grams of product was obtained for which the theoretical yield was calculated from a reaction in which the theoretical yield was calculated to be 10.600 grams. Can you calculate the percentage yield? You just need to recall the formula correctly. Plug the numbers in. Pause, complete. Come back to check. Okay, so I'm going to reveal. So 6.663 is the actual. The theoretical yield was 10.60. Express that as a fraction, times 100 gives you 62.5%. Let's look at problem number 2. This time we're supplied with an equation. If the maximum theoretical yield of ammonium sulfate was 114 grams and the actual yield was 110 grams, calculate the percentage yield. Pause, do the calculation, come back. So I'm going to reveal, remind you of the formula, actual yield over theoretical yield. So 110 divided by 114 times 100 comes to 96.5%. Slightly more taxing problem. Calculate the percentage yield for the reaction between iron 3 oxide and carbon monoxide according to this balanced chemical equation. Given that 15.96 grams of iron oxide produced 4.8 grams of iron in excess carbon monoxide. So in excess carbon monoxide tells you all of the iron oxide reacted, it is the limiting reactant. So you can produce the moles of product based on the moles of iron oxide. Okay, so percentage yield, pause, complete, come back to check. Okay, so first point, of course, is that we need a mole ratio. It's 1 mole of iron oxide to 2 moles of iron. We've got 15.96 grams of iron oxide, so we need to turn that into a numbers of moles. So we divide by the molar mass, so that's 0.1. In theory, we will get 0.2 moles of iron. So that is the theoretical yield, a 1 to 2 ratio. 0.1 would produce 0.2 in theory. But we are given a measured mass of iron that is actually produced. So the actual moles of iron uses that mass, 4.8 grams, divided by 55.8 gives us 0.086 moles. We then plug in to our percentage yield formula. Theoretical, 0.2. Actual 0.086 times 100 comes to 43%. So let's look at a slight variation of the percentage yield problem. Calculate the actual mass of methanol, CH3OH, formed by the complete reaction of 8.6 grams of hydrogen, according to the equation below, given that the percentage yield had a value of 52%. So we know the mass of hydrogen, we know the percentage yield. What therefore would be the actual mass of product produced? Pause, think it through, attempt a solution and come back to check. Okay, so I'm going to go through my answer. First of all, of course, we've got a 2-to-1 reacting ratio of moles in the stoichiometry, the balanced chemical equation. So 2 moles of hydrogen react to form 1 mole of methanol. We need to know how many moles of hydrogen were actually reacting. Well, we're told it's a complete reaction of hydrogen. So we know that hydrogen is fully reacted. So 8.6 divided by 2 gives us 4.3 moles of hydrogen. Theoretically, on a 2-to-1 ratio, that would produce 2.15 moles of methanol. So we got a theoretical numbers of moles of methanol, which we can put into our equation. The unknown in this case is the actual moles. We know the percentage value. So 52 equals the actual moles divided by the theoretical moles, which is 2.15, times 100. So we're going to solve for actual moles. That comes out as 1.118 moles of methanol, and we want to know the actual mass. So having got the actual numbers of moles, we simply multiply by the molar mass, 32, to produce the mass of methanol. So it all centers around this equation here. Percentage is actual moles divided by theoretical moles times 100. As long as you know 2 of the components, you can solve for the third. Atom economy. Atom economy is a relatively new concept devised in an American university involving the green chemistry movement. So it compares the masses of all the atoms in the desired product. So there's a concept, the desired product. So we need to identify in any chemical reaction what is the product that is going to be used or is intended to be made. And we compare the mass of all the atoms in the desired product to the masses of all the atoms that go into the reaction, that is the masses of all of the reactants. And we can do that by looking at the molar masses. So the sum of all of the molar masses of the desired products divided by the sum of the molar masses of all of the reactants is our proportion, our fraction. We multiply that by 100 to give us percentage atom economy. So it's a simple formula that needs to be applied. Of course, the higher the percentage atom economy, the fewer atoms that are wasted. So this is where we get a relationship to the green chemistry movement. That means fewer atoms are discarded into the environment. So let's do a model. We need to identify the desired product. In this case it is iron, which is extracted from iron oxide by a reduction with carbon. The co-product is carbon monoxide. That is a waste product. It's released into the environment. The balanced chemical equation is shown below. So to calculate the percentage atom economy, we need to do two things. Initially, get the sum of the molar masses of the desired product and the sum of the molar masses of all of the reactants. Now, because we've got two ions, a mole ratio of 2 in the equation, we need to multiply the molar mass of iron by 2. So we include the multipliers in working out the sum of all of the desired product. Similarly, we've got 3 carbons, so we have Fe2O3, 59.6, and then 3 carbons comes to 195.6. Produce the formula for the atom economy, which is simply the desired product, sum of all the molar masses 111.6, divided by the sum of the molar masses of all of the reactants comes to 195.6. Express that as a percentage 57.1. So here is a problem for you to attempt. Titanium is extracted from titanium 4 chloride by displacement by sodium, according to this balanced chemical equation. Calculate the percentage atom economy for this process. So if it isn't clear to you, titanium is the desired product. Pause, calculate, come back to check. So I'm going to reveal the sum of the desired product. Well, we simply have 1 titanium, so we don't need to do any multiplication. 1 times 47.9 is the relative atomic mass, or the molar mass I should say, of titanium. Then for all of the reactants, we do need to take account of the multiplier of 4, so that has to be included in working out the mass of all of the reactants, the sum of the molar masses of all of the reactants, to be precise. So 189.9 for titanium 4 chloride, 4 times 23 comes to 281.9. Plug that into the atom economy equation. Desired over all reactants comes to 16.9%. So here is a second problem. Calculate the atom economy for the industrial production of methanol, which we met earlier in the lesson in terms of percentage yield, according to this balanced chemical equation. So pause, calculate the percentage atom economy, and come back to check your answer. So I'm about to reveal. The sum of the molar masses of the desired product is 32. The sum of the molar masses of all of the reactants, well, we've got 2 hydrogens, so we need 2 times 2 plus 28 for carbon monoxide, also comes to 32. Therefore, when we plug into the atom economy, percentage atom economy equation, 32 is divided by 32, which gives us 100%. So some of you may have spotted it initially. If you've got one product, it must follow that the atom economy is 100%. So that will always be the case. So percentage yield and atom economy both contribute to the idea of sustainability. Sustainability is going to involve both percentage yield and percentage atom economy. So if we compare the production of iron to titanium, for example, we calculated the percentage atom economy for both. The percentage atom economy for the production of iron is 57.1%, whereas for titanium it's 16.9%. So the production of iron wastes less atoms. So that means less atoms are released into the environment, so that is more sustainable, there is less pollution. It's also more economic. Of course, wasted atoms are atoms that have been paid for in one way or another, possibly both financially, but also in terms of energy. So if we also then include the idea of percentage yield, well, a high percentage yields means that in practice, less material is lost in the process. So in our lesson earlier, we had a relatively low percentage yield, and the second problem took us to a relatively high percentage yield. The high percentage yields mean that less material is lost, and therefore to get a certain amount of product we need less reactant, so that is both more sustainable but it's also more economic. So industrial processes, in an ideal world to which we are as chemists trying to work towards, industrial processes would have both a high percentage atom economy and a high percentage yield, for both the reasons of sustainability but also in terms of the economics of the process. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.